The history of Earth's moon is a tale of cosmic catastrophe and planetary evolution, rooted in a dramatic event that reshaped our planet's destiny. Around 4.5 billion years ago, during the early stages of the solar system, a colossal collision occurred between the young Earth and a Mars-sized body known as Theia. This cataclysmic impact, often referred to as the giant impact hypothesis, not only led to the formation of the moon, but also played a pivotal role in the development of Earth's geology and atmosphere. As debris from this collision coalesced into our moon, it began a journey that would profoundly influence the tides, stabilize Earth's axial tilt, and ultimately support the emergence of life. This extraordinary sequence of events laid the foundation for the moon's complex and fascinating history. Number 4. The early solar system and the giant impact hypothesis. The story of Earth's moon is a fascinating tale that begins in the chaotic early solar system, approximately 4.5 billion years ago. During this time, the solar system was a tumultuous place, filled with countless planetary bodies and debris orbiting the young sun. These celestial objects frequently collided with one another, a process that played a critical role in shaping the planets we know today. Among these nascent planets was the young Earth, which was still in the process of forming and cooling from a molten state. A prevailing theory about the moon's formation is the giant impact hypothesis. According to this theory, the moon was created from the aftermath of a colossal collision between the proto-Earth and a Mars-sized body, often referred to as Theia. This cataclysmic event is thought to have occurred roughly 100 million years after the solar system's formation, during a period known as the Late Heavy Bombardment. The impact was so intense that it vaporized Theia and a significant portion of Earth's outer layers, ejecting an enormous amount of debris into space. The debris from this colossal collision gradually coalesced due to gravitational forces, forming a ring of material around the Earth. Over time, this ring of debris began to clump together, forming larger and larger bodies. Eventually, these bodies merged to form the moon. This process of accumulation, known as accretion, took place over a relatively short period of time, geologically speaking, and resulted in the moon as we see it today. The newly formed moon was much closer to Earth than it is now, and it has been slowly drifting away due to tidal interactions ever since. Number 3. The formation of the moon. In the aftermath of the colossal collision between Earth and Theia, the debris from both celestial bodies was ejected into space. This debris consisted of vaporized rock and molten material, primarily from Earth's mantle and Theia's crust. Under the influence of gravity, the ejected material began to orbit Earth, forming a vast disk of debris around the planet. This disk, rich in silicate minerals, slowly cooled and solidified, initiating the process of accretion. As the material in the disk continued to orbit, it began to coalesce into larger clumps, gradually growing through repeated collisions and gravitational attraction. This process eventually led to the formation of a single large body, our moon. The moon's composition provides critical evidence for the giant impact hypothesis. Studies of lunar rocks brought back by the Apollo missions reveal that the moon is primarily composed of silicate minerals, similar to those found in Earth's mantle. This similarity suggests that the moon's material was largely derived from Earth, supporting the idea that it formed from the debris of a massive impact. Furthermore, the The isotopic compositions of lunar and terrestrial rocks are remarkably similar, indicating that the Moon and Earth share a common origin. When the Moon first formed, it was significantly closer to Earth than it is today, possibly only about 20,000 kilometers away, compared to the current average distance of approximately 384,400 kilometers. This proximity resulted in strong tidal forces between the two bodies, which had profound effects on both the Moon and Earth. On the Moon, these tidal forces caused internal friction, leading to intense volcanic activity and the early formation of its distinctive lunar maria, the large, dark basaltic plains that are visible from Earth. These volcanic features are primarily found on the near side of the Moon, facing Earth, suggesting a complex interaction between tidal forces and the Moon's geological activity. Number 2. The Moon's geological evolution. The Moon's surface reveals a rich history of volcanic and tectonic activity, followed by a long period of relative geological inactivity. This history begins with the early Moon, which was enveloped in a vast ocean of molten rock, known as a magma ocean. This magma ocean was a result of the intense heat generated during the Moon's formation, likely from the energy released by the impact and the subsequent accretion of debris. As the Moon gradually cooled, this magma ocean began to solidify, leading to the formation of the Moon's primordial crust. During this process, heavier elements and minerals, such as olivine and pyroxene, sank towards the Moon's interior, forming its mantle, while lighter materials, primarily a north acidic plagioclase feldspar, floated to the surface, creating the crust. The lunar surface is dominated by two primary types of terrain: the large, dark plains known as maria, and the brighter, heavily cratered highlands. The maria, which cover about 17% of the lunar surface, are vast plains of basaltic rock that were formed by ancient volcanic activity. This volcanism occurred billions of years ago, during a period when the Moon's interior was still hot enough to produce magma. The basaltic lava from these volcanic eruptions filled large impact basins, which were created by collisions with asteroids and comets during the Moon's early history. These impact basins, such as the Imbrium, Serenitatis, and Crisium basins, are predominantly located on the near side of the Moon, which faces Earth. The near side of the Moon has a thinner crust compared to the far side, which allows magma to more easily reach the surface and form the extensive maria. In contrast, the far side of the Moon, which is less familiar to us because it is not visible from Earth, is characterized by a thicker crust and a different geological history. This thicker crust impeded the ascent of magma, resulting in fewer volcanic plains and a greater abundance of heavily cratered highlands. These highlands are composed mainly of anorthositic rock, which is rich in plagioclase feldspar, giving them a lighter appearance compared to the basaltic maria. Number 1. The Moon's influence on Earth. The Moon has had a profound impact on Earth's environment and the development of life, primarily through its gravitational influence. One of the most noticeable effects of the Moon's gravity is the creation of tides. The gravitational pull of the Moon causes the Earth's oceans to bulge outwards on the side closest to the Moon, creating a high tide. Simultaneously, another high tide occurs on the opposite side of the Earth due to the centrifugal force created by the Earth's rotation. These tidal forces result in the regular rise and fall of sea levels, a phenomenon that has been crucial in shaping coastal ecosystems and the development of marine life. Tides have played a significant role in the evolutionary history of life on Earth. The regular movement of water creates intertidal zones, areas that are alternately submerged and exposed by the tides. These zones are rich in nutrients and provide unique habitats that have fostered the evolution of diverse life forms. Many marine organisms have adapted to the rhythmic changes of the tides, developing specialized features and behaviors to survive in this dynamic environment. The mixing of ocean waters due to tidal movements also helps distribute heat and nutrients, influencing oceanic currents and climate patterns. Beyond the immediate effects of tides, the moon plays a crucial role in stabilizing Earth's axial tilt, also known as obliquity. Earth's axis is tilted at an angle of approximately 23.5 degrees relative to its orbit around the Sun. This tilt is responsible for the changing seasons, as different parts of the Earth receive varying amounts of sunlight throughout the year. The moon's gravitational influence acts as a stabilizing force on this axial tilt, preventing large and chaotic shifts that could occur due to gravitational interactions with other celestial bodies, such as the Sun and other planets. This stabilization is vital for maintaining a relatively stable climate over long periods. If Earth's axial tilt varied significantly, it would lead to extreme changes in climate with severe consequences for the planet's environment and the life it supports. For instance, a greater tilt could result in more extreme seasons, with hotter summers and colder winters, while a lesser tilt could reduce seasonal variation, affecting ecosystems and agricultural cycles. The moon's role in Earth's environmental stability and the development of life underscores the interconnectedness of celestial bodies in our solar system. It highlights the delicate balance that allows life to thrive on Earth, influenced not just by our planet's own properties, but also by its relationship with the moon and the wider cosmic environment. This understanding enriches our appreciation of the moon's significance beyond its physical presence in the night sky, recognizing it as a key factor in the history and continued existence of life on Earth. Thanks for watching! Don't forget to like, comment, and subscribe for more!